Okay, great. Cool. Can you see my screen?
Yes, sir.
Okay. So we will do some recursion problems since recursion was taught last week and we haven't talked about it in our help sessions. So let's start with a simple loop, right? So for example, this is a program that um, calculates the sum of from 1 to n. So the way this works is, so this was also introduced in lecture this time. Basically, you can pass arguments to main, and we can. So the first argument that we pass, we are assigning it to n, and since the argument is a string, we are converting it into a long. So that's why we have this a to l function here as chi to long. So then there is a simple loop that goes from 2 to n and computes the sum. So let's run this and let's say 10. So sum of 1 to 10 is 55. That sounds about right. 100 is 5050. Okay. So we can write the same program in recursion as well. So we can say int sum, and let's say it takes a number, and let's say these are long ints, and then it returns n plus sum of n minus 1. So is there any problem with this program that I wrote?
Yes, sir.
Okay, and what is the problem?
So it will not stop anywhere. It will go infinitely because there is no stopping condition there.
Yeah, exactly. So since there is no stopping condition, it will keep on calling itself. So we need to add a stopping condition. So let's say our stopping condition is if n is 0, then I'll return 0. Okay, let's run this. Oops. With 10 and it outputs 55. So this is also correct. Okay, great. So now let's run the same program with large numbers. So let's run it with, let's say 1000. So 1000 works, 10,000 works, 100,000 works, 1 million. When we go to 1 million, it starts crashing. Is segmentation fault? So any thoughts like why when we increase the number of, when we increase n, it crashes after some point?
So actually, what we mean is this segmentation fault error. Is what actually has happened.
Yeah, so segmentation fault means you try to access some memory which you didn't have, right? So this is an error related to memory. So when you go to large numbers, this program is crashing. But we can look at the for loop one. Right, I just reverted the code to go back to for loop. In for loop, if I run the same program with the same large number, it actually works. So there's something to do with recursion, because of which when you run it with large inputs, the program is crashing. So this was discussed in the class actually. Does anyone remember why for large inputs the program would crash?
Sir, I think because the recursion, it is called multiple times, so it is stored in stack, so the stack overflows or something. There are too many, the depth is too much for the memory.
Right, exactly. So let's look at how a recursive program executes. So let's see, we are entering this, and let's say here we are exiting here, and let's say output is this, and we return the output. And we are also exiting here, right, for 0. Right, so I added some printf which will show us when a program, when a function, when this sum function is entering and exiting. So let's look at how this program is executing. So I'll compile this again, and let's run it for a small input. So basically what happens is in recursion, open the program side by side. Okay, so so what is going on is we called this sum with 5. So it came here, it printed 5. Then 5 is not equal to 0, so it came here, and then it did a recursive call with 4. N minus 1 is 4. So it will come back here and it will print entering 4. So entering 5, then entering 4. Then similarly, it will keep on printing entering 3, 2, 1 until it reaches the stopping condition, which is entering 0. When it reaches 0, then it prints exiting 0. So then basically it is coming out of 0, and then it will go inside 1. Then it will come out of 1, then it will go inside 2. So basically, if you think about call stack, right? So we have 5, then 4, then 3, then 2, then 1, then 0. And then when we return, we remove 0, then remove 1, then 2, then 3, and so on. So basically, when you have more numbers, if I run it on a large number, then the number of entries you have to put in call stack is increasing, right? So in this case, like we ran it with 5, so we had 6 entries in the call stack. But if I run it with 50, we will have like 51 entries in call stack, right? From 0 all the way to 50. So that's why after some point, so since this call stack is taking memory, after some point there is no memory to give to the program, and it basically crashes. So we can try to measure like how much memory is available, right? So let me comment this out. And let's run this again. Let's make sure this works. Okay. So we can do some sort of search to figure out what is the maximum number we can run it with, right? So let's say this is 100,000, 1 lakh. So this works fine. 1 million doesn't work. So let me half it. 500,000 doesn't work. Let me half that. 250,000 doesn't work. So 125,000. Oh wait. Okay, 125,000 works. Let's try 200,000. This doesn't work. 175,000 also doesn't work. 150,000 works. So roughly speaking, we are able to run this program up until 150,000, right? So next we can try to look at the assembly program. So when we look at this is assembly program, we don't have to understand everything. But basically something to understand is this is roughly allocating 16 bytes in the memory for this function called sum, right? So this is, we are inside the sum function, and this is allocating 16 bytes. So basically the total amount of stack space that we have available on this machine seems to be 16 times 150,000, which comes out to about 2.4 MB. Right, so you can try this experiment on your own machine, like write a recursive program. Actually, I am surprised it is 2.4 MB. I think it should have been 4 MB. Let's try to. I wonder if this variables are taking some space, extra space as well. So let's see. Let's write a very simple recursive program. Right, so this is also a recursive program. Now we will run this program. And let's see what inputs it can work with. Okay. 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 So it works till 250,000. Let's see, 300,000. Okay, so it roughly works till 250,000. And 250,000 multiplied by 16 is actually 4 MB of space. So on x64 laptops, generally the stack size is 4 MB. Right, so you can repeat this kind of experiment on your own machine to see like how much stack space your machine is willing to give to a program. Cool. So coming back here, any questions so far?
Sir, what is the S flag that you used in GCC?
Yeah, S is for printing this thing. So S is for printing the assembly code. We looked at this loop.s, right? So by using dash s, it will also output a dot s file, which is basically the assembly code of the program. Okay, cool. Any other questions? Cool. So I hope you understand how recursion is working. So basically it is working in a stack form, right? So it calls calls the recursive function, and then the inner function has to exit before the outer function can exit, right? So until 4 exits, 5 cannot exit. So this is generally true. This is true even beyond recursion, right? So when a function A calls function B, A cannot exit until B exits. So first B will exit, and then A will continue running, and then A will exit. So in the recursion, it's the same thing. Just the only difference is you are calling the same name of same function instead of a different function. Cool. I hope this is clear. Okay, so one thing is, so this is pretty bad, right? It looks like recursion is not very useful. Like the programs are much simpler to write. So look at, let's compare these two programs. So one is a for loop and another is the recursive function. And if we look at the recursive function, it's so much simpler to write. So this is a very small thing we are trying to do here. So you may not appreciate it yet. But when you build like larger programs, you will start to see that these loops and all become complicated, especially when you're doing like some data structure work like trees and lists and whatnot. So recursion simplifies your logic a lot. Like in this recursion, we were just saying, okay, if n is 0, then it is 0. Otherwise, it is n plus some n minus 1. So this logic is much, much simpler to think about than the loop. Um, but in this case, like it's, since it is a very simple problem, you may not appreciate it. But recursion is many times much simpler to write. But the problem is, so we need to be careful about the depth of the recursion. Like how big is the input? If the input is too big, then your recursion will crash because of stack size issues. So there is one other approach to make the recursion work. So let's see. So I'll write a different implementation of sum. Sum tail, let's call it. And let's say this takes a running sum. Let's say s. So this is the sum we have found so far. So when n is 0, then we return s. Otherwise, we return n minus 1 and n plus s. Right? And then when I call it, I call sum tail n comma 0. So basically, when you start the recursion, the sum we have found so far is 0. Then when it goes in, let's say n is 5. So it will say, okay, so here, let's say it will call with 5 comma 0. Right? So here n is 5, s is 0. So then here n minus 1. So the next call will be with 4 comma 5. Right? And then the next call will be with 3 comma 9. And then the next call will be with 2 comma 12. Right? And so on. So first of all, yeah, let's run this and convince ourselves that this is actually doing what the sum is doing, what the sum method was doing as well. So I will print out with the sum and I'll also print out with sum tail. Okay. And let's say I run it with 50. Oops, what happened? What did I mess up? Went into an infinite loop, it seems. Interesting. If n is 0, then I'll return s. Otherwise, okay, let's do it one at a time so we know which function is wrong. Okay, sum has an infinite loop. If n is 0, return 0. twice return. This looks okay to me. What? Interesting. Oh, shoot. I have a scanf here. Okay. Okay, so we printed something from sum and we also printed from sum tail, and they're both giving same output. So it seems they are doing the same thing. So any questions so far? Do you follow what this sum tail is doing? Hello.
Yes.
Okay, great. Cool. So now let's let's run this and see what happens. So I'm going to remove sum, and then I'm going to change things a little bit. I'll put a dash O flag while compiling, and I'll tell you what this is in a bit. And now let's run this with large inputs. So I'm running it with 10,000, 100,000, 1 million, 10 million, 100 million, 1 billion. So it seems like this is working fine. This is not crashing, which is interesting, right? So even though this is a recursive program, and we learned that in recursion, because of stack, when you have when you put things on stack, at some point the stack size will limit you, and at some point you will crash. But in this case, we are seeing that actually it is not crashing. So what we did here is basically we used a different kind of recursion, which is called tail recursion. So basically, if you think about it, right, like since sumtail is the last call, and there is nothing that needs to happen after sumtail returns. So when you call 5,0, then 5,0 is about to call 4,5, right? So we can just put it in the same space instead of creating a new space, because we don't even have to come back to the previous function, right? Because whatever this returns is the final output anyways. Compare it with the previous case. In the previous case, when it was sum 4, then I need to return back, add 5 to it. So because it is n plus sum 4, and then return to the main function. So that is why I need to have the stacking 5, 4, 3, 2, 1. But in tail recursion, you don't need stacking, because you don't need to put a extra activation record, because you can just return whatever the other function is returning. Right.
So, sir, so when the return statement only calls the function again and does not have any other like plus n or something, so it will go by the tail method.
Right. Exactly. So let's try to break this, right? Um, so let's say this is long output, and let's say I add this another small thing here. Right. So now we cannot use tail recursion, right? Because when 4,5 returns, it has to come back to 5,0 and then print what 4,5 returned, right? So let us try to run this. Okay, so now it has started crashing again. right? So at 1 million it crashes. Oh my god. Yeah, at 100,000. So it is printing. This is printing in every recursive call. So that's why we have so many prints. But the point was this is crashing again because this is no longer a tail recursion, because you have to keep 5,0 stacked so that when you return from 4,5, you can come back and do a printf. So because of this printf, we had to keep all these stacks. But when we didn't have the printf, then you don't need this stack. You can just directly call the new function in the same stack space. So this is a very, very cool, interesting thought. Right. So now after I remove printf, it actually works. So let's see what happens with sum, right? Let's see what happens with sum. So sum, when we were compiling it without the -o flag, sum was crashing, right? So let's compile it with the O flag and run it through. So this is 100 million. So with the O flag, actually sum also works fine, right? And we have exceeded the long int space, but basically the sum is working fine. So the thing is, this -o is asking the compiler to do some additional optimizations than what it generally does. So essentially, when you pass this -o flag, compiler is turning your recursive function into a tail recursive function, right? So it is basically going to take this function and try to convert it into a sum tail like function, or it can even try to change this recursive function into a loop internally. So -o flag is basically asking the compiler to do some additional optimizations than what it generally does. Yeah, so these were some ideas, some pretty interesting ideas. So any questions so far?
Sir,
Mm-hmm.
so can you please again explain when we called the sumtail function, then why it was not behaving like a normal stack function, normal recursive function?
It is behaving like that, but basically it's an additional optimization that you can do, right? So let's say, so let's go back to the original one, right? This was our original program. So when you're calling, so basically let's think about call stack, right? So our call stack will be our call stack will be at the bottom. We have 5,0, right? So that is the call that the main is making, right? It is saying n is 5 and accumulate, and s is 0.
Yes, sir.
Then when the recursive calls happens, n minus 1 comma n plus s, this call is going with 4 comma 5, right? Then this call is making another recursive call to 3 comma 9, another recursive call to 2 comma 12, 1 comma 14, and 0 comma 15, right? And then finally, so this is how your functions are sitting on top of each other in general in recursion, right? And then when you see that n is 0, so then this returns. So this returns back to 1 comma 14. Then this returns back to 2 comma 12, which returns to 3 comma 9, and then so on, right? But the thing is, in this case, you don't need to keep 5 comma 0 in memory, right? When you're calling 4 comma 5, because look at this. Whatever the value 4,5 returns, 5,0 is just going to return the same thing, right? It is not going to do any extra manipulation on it. So you don't need to keep its local variables. You don't need to keep anything pinned to the memory, right? Comparing that with this one, right? So in this one, in this one, when 4,5 returns, right? So assuming all of these have already returned, when 4,5 returns, when it comes back to 5,0, you still have to add this n to whatever is the output of 4. Sorry, there's no, this doesn't have a, right? This is only a single parameter function. So when sum 4 returns, you have to add 5 to it, right? So
Yes, sir.
right, so you have to keep this call with 5 pinned to the memory because there are some additional operations that you have to do. But in this case, in the tail recursion, basically there are no additional operations you need to do. So you can just reuse the same space. So in the space on which 5,0 was allocated, you can call 4,5 on the same space. Then you can call 3,9 in the same space. So this is just a optimization which is only possible in this tail recursion.
So in this method, finally 0,15 will be returned to the main function.
Sorry, say that again.
So finally 0,15 will be returned to the main function in this case.
So return value is only long, right? There's no there's only one value. So yeah, 15 will be returned to the main function because this
But how that is decided that 15 will be returned?
because look at your stopping condition, right? So in stopping condition, it is saying when n is 0, return s. So
but at that time s will be 0, no?
no, s is
S
15.
is not changing.
S is
Okay,
changing.
okay. S is changing.
Yeah, n plus s, right? So this is the recursion. So we start from 5,0, then we call 4,5, 3,9, 2,12. So s is changing. So when you hit the stopping condition, then your answer is already in s. Okay, so this was I guess, yeah, the promise is to not teach new things in health session, but
Sir?
yeah.
Sir, when we are returning this n minus 1 comma n plus s, so how is the value of s getting stored and changed every time?
Yeah, so that goes back to how the recursion works, right? So let's look at the simpler example first. So in the simpler example, the first call is with 5, right? So main
Yes,
called it with 5. And then in the next case, we called it with sum n minus 1. So 5 will call with 4, right? And then 4 will call 3, then 3 will call 2, and so on, right? So the value of n, every time this function is called, the value of n is different, right? So coming back here, was this clear? Like 5, then 4, then 2, then is this part clear?
yes, sir.
Okay. So then coming back here, so initially the first call happened with 5, 0. So n is 5, s is 0. So in the next call, what we did is we called it with n minus 1, n plus s. So basically the next call will be with n is 4 and s is now 5, right? Because we did n plus s, right? And then the next time we will do again 4 plus s. So the next time the call will be with 9. Then we will do 9 plus 3.
Sir, when we perform 4 comma 5, we go to 3 comma 9. Then how does the computer know that it has to add 4 to 5?
Because it's n plus s, right? So basically, let's look at the execution when n is 4. and s is 5, right? Let's see what happens. So it will come here. It will see, is 4 equals 0? It is not, right? So I will come here.
Yes,
So
sir.
then I will say I will call with sum tail. N minus 1 is, so my n is 4. So
3.
n minus 1 is 3. Then what is n plus s?
4 plus 5, 9. Yes, sir.
Right. And then similarly, we can look at another example. So n is 3, s is 9. So again, it will come here and ask the same question. That is 3 equals 0.
Yes, sir.
Yeah. I hope, yeah, this should be, I hope you follow now. So now it will call n minus 1 is 2, n plus s is 12, because n is 3, s is 9.
Yes, sir. Understood, sir.
Sir,
Yeah.
sir, where is the scanf statement actually from where we are inputting?
Okay, yeah. Good question. So that comes back to how the main takes input. So we basically pass the input directly to main. So main is also a function, just like all the other functions. So sumtail is a function, right? Recurse was a function. So main is also a function, but it's just a special function with a special signature. Because when you run a program, it will look for the main function. It will try to call the main function, right? So
Yes,
so
sir.
in main, the way we pass function is argc is basically count of arguments, how many arguments you're giving to me, and argv is the actual argument. So we can actually try to print these.
So basically, it works like an array, right?
Yeah. It's a
Okay.
array of strings. So let's just try it. Slash n. Right, so now you can give it stuff from here, right? So I am giving it some other additional inputs when I run this program. So when I run it, it is showing that the first input is a dot out, which is binary itself. The second input is this, third is this, fourth is this, and so on. So basically now instead of scanf, you can just I was just calling it with with different numbers, right? So in the original program, I was calling this with different numbers, right? This was the original program. I am taking, so this one expects that it will be given a number. It will turn that string number into a long int by calling a to l, and then it will use that n to compute the sum. So let's try it again. Right, so I gave it the number here. This will go in n, and then it will print.
Sir, sir,
Yeah.
this atoll function, what is this? Like, I didn't know about this.
Yeah, Yeah, so this was also covered in the lecture. So this is a function that is defined in stdlib. So what this means is basically sky to long. So you have a string. So argv is a character star is of type character star, right? So basically it is a string. So what this is saying is try to convert this string into a long. And then we can also try to write this function on our own. So let's say a to L, it takes a character star, str, right? So we have a long int output equals 0. So we can first try to find length. Right, we have the length of the string now. So then we can go in the backward direction. So int I equals len minus 1, I greater than equals 0, I plus plus. Then we can say your output is equal to str I minus 0 and I can go in the positive direction, I think. Right, so this is basically just taking taking what is in the string and converting it into a number.
Okay, sir.
Yeah.
Sir?
Yeah.
Sir, in the sum till function, sir, do we have to define s equal to 0 first? Initialize s equal to 0?
Yeah, that's what we do here. When we call it with s equals 0.
Okay, sir. Okay, sir. Thank you, sir.
Okay, cool. So now we can look at more recursive programs. Yeah.
So how the stack works in sumtail function, like first 5,0 is there in the stack, then it is replaced by the 4,5.
Yes, exactly.
And then 3, 3, okay. Thank you.
Yeah, I'm now realizing I'm not supposed to teach new things in help session, but maybe this will be covered in the lecture again. So
Sir, I have a doubt regarding main function. So do we have any constraint on what we can input in main? Like over here we are first inputting the number of inputs and the other one is a pointer array, right? So is there any restriction?
I mean, whatever you can type here, you can put there. So there are no restrictions as such.
So उसमें कितने पैरामीटर डाल दो, मतलब 3-4 पैरामीटर डाल दो और
Yeah. So when you look at, if you look at other, जैसे अगर आप इनके जो लिनक्स के कमांड्स होते हैं उनके अगर आप डॉक्यूमेंटेशन देखोगे तो you will find they take many parameters, right? So like this is a find command. So this takes dash h. This can take lot of parameters, even expressions and whatnot. So let's see, there are examples. Yeah, these are some examples of using this command. Like we don't care about what this is doing, but basically this will be implemented in the similar manner. By the main of find will be taking argc and argv, and these things will basically go into argc and argv. So as we can see, you can put random pretty complicated stuff in there.
Okay, sir.
Yeah. ls is another example. Okay, there are no examples here. Okay. No examples, but yeah, to answer your question, yes, you can put as many. I mean, until basically this, again, if you put like millions and billions of things, like until your computer runs out of memory, you should be okay.
Okay, sir.
Okay, I think we can practice a bit more on recursion. So we had looked at a couple of help sessions before. We were looking at palindromes. So we can try to code up palindromes in a recursive manner. Okay. Right. So this one, what it was doing is, so palindrome is, it's, let me make this work first and we can discuss. Okay. So palindrome is basically words which are same when you look at them in the forward direction, and they are same when you look at them in the backward direction. So as we can see, madam is a palindrome because this M is same, A is same, and D is the same. Similarly, like sir is not a palindrome because yeah, and then cis is a palindrome, right? So we had written uh, a loop-based implementation of palindrome. So in the loop-based implementation, what it does is it goes in the forward direction. It has two iterators. One is going forward, one is going backward. And okay, let's not worry about spaces. Yeah, so one goes in the forward direction, another in the backward direction. And then we check if the forward and backward are not the same, then we can just print it is not a palindrome. And we keep doing this until forward is before backward. So that is why we have the stopping condition as forward is before backward. So so as we can see, like initially for madam, for example, forward will be on the first M and backward will be on the second M. Then we will compare these two M's. If they are okay, we will increase forward. So forward will go to this A, and backward will go to this one, this other A. So we will increase forward and decrease backward. So we had written this palindrome function last time, or last time. So we can try to write it in a recursive manner and see how easier it gets. So I can do in palindrome char star, and I can just say, and let's say I'm also passing it the length, right? So I'll find the length here and pass it the length. So all I have to do is in the base case, I just check if string 0. So first of all, if the length is less than equal to 1, right, then we know that it is a palindrome, right?
Yes, sir.
And I can just return. Otherwise, I can say, oh, we have not studied pointers. This will be a problem. This will be a problem. Okay, we will have to use pointers to make the recursive call.
So can you please briefly tell us about pointers?
Yes, sir. Please tell it about it.
I think it is best if it is introduced in the lecture, but I can tell you the basic idea. So basic idea is every variable is resident in memory, right? So you can imagine your memory is just a sequence of addresses, right? So think about memory as a street, right? Whatever street you live in, or let's say IIT Delhi main road. So you have at a particular address, you have one building, then another address, you have another building, another address, you have next building, and so on, right? So you can think about memory as just a long road that keeps on going until like 4 GB or whatever is your total memory, and it starts from 0 to all the way to, and the basically the addresses of the houses or whatever you want to call it, address of the memory blocks are starting from 0 all the way to your 4 GB or 8 GB, whatever your memory is. So basically pointer is nothing but the address of a variable. So if I store a variable here, the pointer of the variable is saying that this variable is stored here. So if you think about, let's say I am a variable, then my pointer is the address on which I am sitting right now. So pointer is nothing but an address of the variable.
So for example, each time we define an integer variable, automatically some variable is defined which is the pointer to that integer variable. Is it like that?
No. So that is a very good question, and that is generally the most confusing part about pointers. So if you do that, then you are infinitely using memory, right? Like if you can do it recursively. So when I put a variable, then I also have to store the pointer of the variable, but then this is now also a variable, so I'll have to store the pointer of pointer, but
Yes,
now,
sir.
right? So this is not how it works. So the way it works is compiler will just put it, or OS will just put it somewhere, and then you can ask for the address. So when we say like ampersand n, like in scanf, right? So this is saying, tell me the address of n. Where is n? So what this returns is actually a pointer to n. And now you can imagine this is how scanf is working, right? So scanf just needs to know where I need to fill the value in the variable. I don't care about anything else. You just tell me where to fill whatever the user is inputting. So you can find the pointer on demand of any variable by using this ampersand. But in general, this is not stored anywhere. You can choose to store it in your programs, but it's not done by default. Okay, so let's let's not do palindrome. I think we can do like Fibonacci one, because it's a little bit different type of recursion. So what this says is if n is 0, then I'll return 1. If n is 1, I'll return 1. Otherwise, I'll return Fibonacci of n minus 1 plus n minus 2. Let's say now it's in 10 and printing. Right, I'm now taking the input and then I'm printing the Fibonacci. And in Fibonacci, now this is a different kind of recursion. So there is n minus 1. So Fibonacci number is sum of previous two numbers in the sequence, and the sequence starts from 1, 1. So that is why we have two stopping conditions, and then we have a recursion. So I run this. The Fibonacci number for 2 is 2, right? So 1 plus 1 is 2. Then 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. So this is a little bit different type of recursion, and we can do the same thing with printing. So let's run it with just 2. So 2 will enter 2, then enter 1, then enter 0. And okay, we didn't print here. So 0 and 1 are base conditions. So right, so in 2, when it comes inside 2, why is it not printing? Oh, I didn't compile it. Okay, so first it will come inside 2, right? So in 2, it will check these if conditions, they are both false. Then I'll check, then I'll call Fibonacci 1. 2 minus 1 is 1. So it will go inside with 1. So after enter 2, it goes inside enter 1. Then 1 will start executing and it will see, okay, actually n is 1. So it will print exit 1 and return. So it will print exit 1 and then return. So when we come back to 2, the 2 will now is done with Fibonacci 1, then it will call Fibonacci 2, Fibonacci 0. So then it will go inside 0, it will finish 0, and then it will exit on 2 as well. So we can look at 3. So 3 will go inside 2. 2 itself is a recursive call which will do 1 and 0. And then we'll exit 2. Then we enter 1. 1 is base condition, so it stops. Then we exit 3. Yeah, so any doubts regarding this, how this works? This is a bit different than the other recursion because we are making 2 recursive calls. Okay.
Sir?
Yeah.
Sir, here the function is decreasing like n minus 1, n minus 2. So why doesn't it takes the negative values like before 0 why doesn't it take those values?
Yeah, so that is why we put the stopping condition.
Okay,
So
okay,
as
okay.
Okay, so I think we are done with recursion. So I'll ask again the question I asked in the beginning of the lecture, beginning of the session. Has anyone built any AI for Pong that they want to test out? Or otherwise we can just keep talking about recursion. Okay, guess not. Cool, that is fine.
Sir,
yeah.
Sir, how can we make that Pong program like the one you make in class? I mean, from by user input in Windows.
You have to install the N curses. I don't have a Windows machine, so it has been a little.
Okay, sir.
Yeah. Okay, if there are there any other questions from the lectures or anything else that I can answer?
Can you tell the AI thing? I tried it, but it worked for some time, but then the computer also failed. Right, like the formula I was using was something wrong.
Yeah, so so this is the default game, default dumb AI that we had written in the last help session. Both the computers are using the same AI program to control the paddles. And then the criticism we had about this AI program. So the way this one works is very simple. Yeah, so what this was saying is if the ball is above the pedal, then move up, then move the pedal up. If the ball is below the pedal, then move the pedal down. Otherwise, stay wherever you are. Right, so let's look at this again. So whenever the ball is moving below the pedal keeps moving below. When the ball is above the pedal is also moving in the upward direction. Right, and the criticism we had for it was basically this doesn't work if the pedal is moving at a rate slower than the at the same rate as the ball, because then the pedal will never be able to catch up the ball, right? So in the previous run that we saw, the pedal was moving at a speed twice as fast as the ball. So when the ball moves, pedal moves twice as much. So that's why it's able to catch up with the ball. But when it is running at the same speed as the ball, it will never be able to catch up, and hence it will fail. So we were discussing like how we can build a pedal that doesn't have this problem. So you can think about it some more, and I have shared this code. So basically my hope is in one of the help session we can, so like many of you will write your own version of this AI, which is much more smarter than this one, and then we can play each other's AI. That will be a lot of fun exercise, and like learn from each other the different logic that we use to build this. And then we can try to complicate the Pong game and then complicate the AI along with it. So yeah, let's keep it at that. Yeah, but hopefully if we have like 5 or 7 different versions, then we can do some kind of a tournament. Yeah. Okay, let me see if there are any other questions. Oh, so Samir, were you able to run it on Windows and Curses? Like the program I had shared. Samir on the call.
Yes, sir. I use WSL2.
Okay, so can you send me your version of the program and I can upload it so others can also use it.
It's actually the same program. I just run it on WSL2.
Yeah, so you must have made some modifications, like slight modifications, right?
No, like I just ran it and it worked.
Oh, really?
Yes.
So maybe send instructions on how to use this WSL2.
Okay, sir.
Yeah. Okay, cool. So that is all I had. Any other questions, comments, thoughts? Okay, there are no questions. Thank you very much. I will see you next week. Bye.
Sir.
Yeah.
Sir, you told us to do some simulation.
You did you do that?
No, sir. You said that we will do that in next help session.
Yeah, I decided against it because recursion is important.
Okay, sir.
Sir.
Yeah.
Sir, I had a doubt. If we have written a tail recursive function, so do we have to like optimize? Do we have to include the O flag, or will
Yes.
it automatically?
You have to use O flag. Yes.
Okay.
So it will work on any type of recursive function.
No. So it has to follow the tail property that it is the last thing that we are calling. right? If it is not a tail recursion, then it will not work, right? So we looked at doing some printf after calling the sum tail, right? And then it was not working.
Oh, okay, sir. Okay, sir. Thank you, sir.
Cool. Thanks, everyone.
Thank you, sir.
Thank you, sir.